Okay, all right. Yeah, sorry about that, but because the conversation was going all over the place, I'm not necessarily following a format. Right? But so for this one, they block in where there's a comparator circuit. And remember how comparators work. If you check one of the early op-amp, there's a thing with zero crossing and positive voltage level and negative voltage level detectors. And what we have done for the multivibrators is to replace this, which could have been a positive V or a negative V, depending on what you did. We replaced it by a little capacitor here that can charge and discharge. So depending on what it's doing, right, we could charge it up, and then if here goes more negative than here, or the value at this input increases beyond this one, this will go negative. If this goes negative, the capacitor will discharge and charge negatively again. And then when it gets more negative than this one, this input will take effect, and then it goes positive, and so the output will toggle between positive and negative all the time, right? And this is a sort of, this is the output here. The limit of this depends on the op-amp. So like if this is plus or minus 9 volts and you're using something like a conventional 741 op-amp, you will probably get this between about plus and minus 7 volts kind of thing, right? And this, of course, is the charge discharge voltage across the capacitor, right? And this is of course related to the value that you set that threshold at. That voltage is set, right? The threshold voltage here set by this, okay? This is here, and you know, well, V out over V out R2 over R1 plus R2, right? So you could shorthand and call that, in the notes, we called it lambda. So that sort of does it, the fractional feedback, if you like. And then the charging and discharging part of it, right? This is fairly easy. We didn't do the derivation. I'm not going to ask you to do the derivation, but lambda is the relationship between that little, is a fraction of the voltage that is coming back here, right? That one. So lambda is R2 over R1 plus R2. Okay. Of course, if you make them equal, right? If you make them equal, then lambda is a half. Okay. And then you could work back from that, and then you get the timing here. And then we went from the Astable to see, okay, let's try and just let it stay, basically stay here. Never mind. So it stays at some kind of thing until I now tell it to do something, and then it will go up and charge, and then come back down and rest again. And that's where the two capacitors come in. Sorry, the two capacitors. This one is to do the triggering to make it start, and then this one is to do the timing together with this to see how long it would stay. All right. Okay, so we had that. So that's fairly straightforward. Let me see what else we had. This was, I guess, the longest explanation. And then so you have 3 of them. You have one where once you turn it on, it's going to do this all the time, right? And this is the astable or astable, meaning not really stable in either state. It will stay here, then it will stay here, then it will stay here, then it will stay here. Then you have the monostable, which is only stable in one place. So it's staying low, minus VSAT. It will turn to positive VSAT for a little while and then come back down. So it is only stable in one place. So this is mono. And then it has one that will stay in one of these states for as long as it will stay low. Then you do something, it will go and stay high and stay there for as long as you want. Then once you do something, until you do something, it's not going to stay. So it's stable in either of these states, and that's a bistable, 2 states, right? The other name for it, of course, is a flip-flop. So once you do something to it, then it will only at that point in time does it change. Okay? And those are the 3. Of course, you're more familiar with the flip-flop in the form of from a digital electronics, you know, the JK flip-flop or the type D, right? This one will work with from plus or minus VSAT. So this is a bipolar type of flip-flop. These go from 0 to plus VCC, usually plus 5 or plus 3.3 volts alone. Okay, so that's a little difference, and all of them have applications around the place. The flip-flop, of course, is you can use for switching applications, of course, on-off sort of applications. The monostable, I don't know if you have come across anything in your microprocessor. Have you come across something called debounce?
I cannot remember.
Right. When you have a microprocessor, right, and you have a switch, like a little push button switch to give an input. Let's say this is to put a low on the input.
Yeah, I remember.
Right. Switches themselves, remember, switches are mechanical contacts. So what happens in here, instead of a nice low, right, going from high to low, what you could get is this kind of juddering on the mechanical contacts of the switch, right? And they call this bouncing. So in other words, the contact is not nice low to high or high to low. It goes and then it chatters a little bit before it settles down. To avoid this kind of thing, what they do is to send it through a monostable. So at the first pulse, it generates a nice clean output and ignores the remaining one for the other bounces for a little time. Remember, we just said that this circuit needs a little time. There's a little time to recover. So once the bouncing of the switch is occurring in this zone here, all of these other positive and negative incursions are ignored. So that so when you press the switch, you get a nice clean single pulse that the microprocessor will now use to reset or to detect some sort of input and do whatever it has to do. All right. So monostables are used a lot in switch debounce applications to clean up mechanical contacts. A lot of and this goes back to, you know, when you connect the real world to circuits, a lot of funny things happen, and all of these little circuits that we spoke about here, many of them, the applications are to sort of clean up that connection between the real world and the electronics.
The analog and digital.
The analog and digital domain, yeah. All right.
So A-stable is 0 to positive VCC, monostable is 0 to positive VCC, and the bistable is positive
but in this
negative.
case, in this case we're using op amps. So it's minus VSAT plus VSAT, right? So the A-stable sits down at minus VSAT, and when you tell it to when you give it the input, it will switch to the positive VSAT for a particular time and then come back to minus VSAT. The monostable will stay in minus VSAT. Sorry, my mistake. The A-stable will start at minus VSAT, after a particular time switch to positive VSAT, then after a particular time switch back to negative and keep going. The monostable will sit down forever in minus VSAT until you give it an input. And when you give it the input, which is a negative going trigger a pulse, it will go to positive VSAT and stay there for a particular time and then come back down again and settle in minus VSAT and stay there, right? The flip-flop will stay at whatever it is. So if it's in minus VSAT, it will stay there until you trigger it. Then it will go to positive VSAT and stay there until you trigger it again. All right?
So like essentially for the Astable, once it is triggered, it will continue pulsing.
Yeah, once you put on power, it will continue pulsing. If you look back at the Astable here, you will see that it doesn't have any input. Right? You have nothing to do with this. Once you turn it on, right? If you just had the circuit powered up and the capacitor is discharged and everything and so on, when you power it up, it will assume a particular state. Okay, if the capacitor is at remember, this is when it starts. This is kind of open loop right here. So the gain is very large. Whatever is the difference in voltage when you power it up, you don't know where it's going to start. It's a sort of is random. So it will start either by putting this to VSAT or sending it to minus VSAT. Right? That is strictly up to the circuit and how the circuit behaves at the point when you power it up. Once it does that, though, it will start going positive, negative, without you doing anything until you switch it off. Right? The only way to stop it is to turn it off, to remove power there. Right?
Just I can't understand the concept of it, right? But I've just one question. Like, when you say power it, you mean by power in the op amp or from the voltage?
Applying power to it.
Okay, no problem. Yeah. Thanks.
Yeah. Yeah. So when I said basically turn on the power supply. So once you turn on the power supply, this thing is going to go, right? It will start somewhere, but is after that it's just going to go positive, negative all the time. All right. The monostable, once you turn it on, it will usually because of how it's wired and the diodes and so on, it will be at negative VSAT and stick there until you do something for it. All right, you go here, so it will start, right? So it will be in minus V out until you tell it to do something. All right, and then the bistable, that one, let me see, at this point, if you power it up, this one, because this is stable in either state, it will either go positive and stay there or go negative and stay there until you give it an input on Vn. All right. So again, it's unknown where it will actually start. The only one that will start on the minus VSAT is the monostable one.
So for the bistable, the input could either be positive or negative, right? And for the monostable, it must be positive.
The monostable, the trigger input has to be positive going negative. You have to give it a negative going signal. Right? That's the trigger.
So the trigger is a negative going positive signal.
A 0 to negative, right? Or a positive to negative, whatever it is. What you need is this diode. For it to work, we have to send here negative so that the diode will turn on.
Oh, yes, that makes sense.
Right? We put it positive, nothing happens.
Yeah.
Right, and it doesn't need to do it for too long. That's what this little network is about. It's really to give you the little the sort of sharp pulse. So you don't have to physically hold this too long. Once you do this, once you send it low, the RC network here takes this and gives you this. Right? And that's all it needs. It just needs this point to go more negative than minus VUT, which would have been at this point in time. Once it goes there, then the thing starts to work again. Right?
One more thing. When you have the negative coming in, right, that little pulse, the output will be negative VSAT or positive VSAT.
Okay, it sits down at minus VSAT until you do something. All right. So where are we? Right. Okay, no, because of how we have the diodes here. This one, the output is positive VSAT. So right. So the output here, this one, the output is at positive VSAT and it's sticking here. When you put the negative input on it, the input now goes to negative VSAT and stays here and then comes back up after a period of time. This is the time here, right? So this is the unstable state here. The stable state is here. In this case, is positive VSAT. If we reverse the direction of the diodes, we could change the polarity.
That makes more sense. So the positive VSAT is the stable state and the negative VSAT is the unstable state.
Yeah, correct. Okay, let me see what else we have here to talk. Right here. So this one, so it's staying here, right? That is the stable state. This is the unstable state here. Right? Once you get a trigger, then it goes here. If we had reversed the diodes, then it would be the other way around. All right? Yeah. Right, and at the end it goes back up positive and it will stick there until you finish with it. Right, so any other questions on this? You all were talking some stuff before I came in. Was it about this?
Yeah.
All right. So, but apart from that, how is your revision in general going?
So for the triangular waveform circuit, right? You could explain how the waveforms is going to be displayed step by step.
Yeah, that is, which one is that? Oscillators or op-amp application?
Let me find it first.
Yeah. Is that waveform generators? Yes, I think that's waveform.
There is operational amplifier applications 2B.
Which one? 2B?
Operational amplifier applications 2B.
Okay, hold on. Let me get that. Select operational amplifier lectures 2B. Right. There we go. Yeah, waveform generators. Sure. Right, so good. Right, so remember what the triangle wave done or does is that it integrating is an integrator and a square wave. So what you have basically, if you go back, the leader plate with a ramp, and the ramp, if you so if you put a step input to an integrator, remember if you integrate a step, right, or UT, right, you get the ramp, the unit ramp, right? And here's the actual circuit that is doing that integration to you. So when you put this step in, it's going to give us our ramp coming out. But because it's we're using the amplifier and we have the input on the inverting, what we have instead of a positive going ramp, we have minus ROT for us, right? So you put a step in, it integrates this step, and if you integrate this, you get the negative going ramp here, right? So what we do now is that we feed back. If I put this step and get a step going this way now, right? So it integrates this step first time, and then it settles. And then if I put this step going this way now, it's going to integrate that, but invert it. So you're going to get a ramp going this way, and then it's going to stay here. And then if I switch this back positive again, it's going to integrate and give me a negative. So if I manually switch it, I get this kind of behavior here, right? And here is when I switch, right? Here I switch, right? Here I switch, then it goes up, and so you keep going, right? So every time you switch, it will go. In fact, I should have had this coming a little bit. This actually was going this way, but anyway, right? So every time you make a switch or put a step, a positive going step give you a negative going ramp, a negative going step giving you a positive going ramp. So if I can make these two, if I don't have no space here, in other words, as soon as it goes negative, if I could switch this in proper time, I could get a positive going ramp at the same time, right? So if I time it right and find a way that as soon as this voltage reaches this point, that the input becomes, that the step input now switches to the from a positive to a negative going step, I could make the thing automatically integrate that, and then it charges up here, and then as soon as it reaches here, automatically switch this input again, and do that, then I'm going to get a triangle wave being created here. All right, fair enough? And the way to do that, of course, is to take the input and find a way to feed it back. So if I can feed the output back to the input, then once this is going in some direction, then I'll have to remove this. Then what will happen is that as it goes back here, it will change polarity all the time. But of course, I can't just simply connect this back to here because it will load down the input and all that kind of thing. So we need to put another op-amp inside here to buffer it. And that is where let that do the comparator circuit first. So here is my integrator before, and now all this is doing, if you forget this bit here and you just made this 10K, right? all this is doing now is looking at you have a ramp voltage coming in inside of here, right? And then at this point you have 0 volts because it's grounded. So this is now looking to see when the voltage comes as it passes through 0, here will toggle, will go in one direction or the other. We have it on the positive side. So when it's going, as soon as this goes more positive than here, the output goes up. The output goes up, that's a step going this way. This, it goes back inside of here. A step going positive means that the ramp is going to integrate and go negative, right? So once the ramp goes negative, it means that this voltage now going this way, right? And as soon as it passes through, remember here's at 0, as soon as it passes through 0 going this way now, this is going to drop. So this is now a step going this way. That is fed back through here. A step going this way integrates, it inverts, so the output starts to go back up again. Right? So as it goes positive, negative, here we have the comparator, and so this is generating an automatic signal for us. And in fact, if you look at it, here, this is what is happening. Right? So that the negative going, well, yes, the negative going step generates a positive ramp. The positive going step generates the negative going ramp. Yeah.
Thanks.
Okay. And in fact, and this is what it looks like if you were to simulate it. If you made the circuit in multisim and put in some, I think it was 1 microfarad and maybe 10K or something. So I put in, this is what it will actually look like.
So from the explanation for that same graph, right, they could show me how the outline will be from the explanation they give.
You mean how you get this from this?
Right. So them say starting at B, right? Then
so we starting here. You have to assume you don't know where the thing is, right? You don't know where they so if we are here if we looking at this point here, then the output of the ramp circuit kind of heading in this direction. All right. So if it is going,
when VRAM crosses VUT, that means it going following up the square waveform, or
no. This is the comparator output. This here is the ramp output here, right? So the ramp output, which is this place here, right? This voltage here, right? This on the way up, okay? This is on the way up. If I forget, I could set the threshold with these two resistors here, but let's just make both of them equal. So it's a 1-to-1 thing, and I have this point that I have here grounded. So let's think here at 0 volts for the time being, right? So all is happening is that as this crosses that threshold, so in this case here, right, I gotta put the threshold. The threshold is really here, which doesn't quite make sense. That's why we have the two resistors in here. But if you understand, as the voltage, as soon as the voltage crosses whatever the threshold is, the upper threshold, as it does that, that signal is now fed back to the integrator, and it integrates that and does this, right? Okay. All I said was to sort of to forget this for the time being. In fact, it's a inverting thing here. So whatever the output here, if I have VRAMP is coming in inside of here. So yeah, if we make this equal, at this point I have here at approximately 0. But just to explain how it's working, right? So as soon as it passes, whatever the voltage is happens to be at this point here, right? And by varying the resistors here, we actually set it to be upper level VUT and VLT, okay, by according to how we pick the values of those resistors here, okay? But just in concept, what was happening is that if I put a voltage here, so if I had a comparator, and I put like 5 volts here, then as soon as the ramp goes more than 5 volts, this will toggle. And then when it's coming back, when it goes less than 5 volts, it will toggle again. Are we setting that particular voltage by how we choose those 2 resistors? Think of it that way. Yeah. Don't overanalyze the circuit. Remember what a comparator does, right? So you have the comparator, I have positive and I have negative. In its raw state as an op-amp, if here is more positive than here, the output going to go up to saturation. If here is less than whatever this is, the output is going to go to negative saturation. I could set this value to whatever I want, right? And by setting that value to whatever I want, then whatever happens at this point, as soon as the voltage here exceeds whatever I have here, then it toggles in one direction or the other. All right, and that is what I'm doing. This point now, so I set this voltage with those 2 resistors, and here is a signal that is doing well. It starts to do this. So as soon as it crosses some lower threshold here, the output toggles, feeds back, and integrates that and does this again for me. And it will just keep doing that once I have power applied to the circuit. Any clearer?
Yeah.
Right.
So then 2 waveforms happening at the same time? Or?
Correct. If you were to connect this in a circuit, you're getting 2 waveforms coming out. So if you hook up an oscilloscope here, you're actually going to get a square wave. And if you hook up the oscilloscope here, right, you're going to get the triangle wave coming, right?
So for the triangle, for the triangle wave, you're connecting it right before the second op-amp.
Mm-hmm.
I believe that was like in a past paper or something, and
yeah, right. So the triangle wave actually coming from this point is coming from here. Right. So again, 2 waveforms out of this. Yeah. So in fact, this is a kind of another way to make a square wave generator or a stable multivibrator. There's another way of making it, right? To use it is a byproduct of the triangle wave, so you could get both the triangle and the square wave coming out of one circuit as it was, right? So it's quite a useful circuit as well. And then, as I mentioned before, you could take the triangle wave and make a very clean sine wave now. If you filter this, you pass this through a filter, one of like the simple op-amp first order filter, right? You pass through that and you put the triangle wave here. If you set a low pass filter, a filter for the low pass frequency for whatever the frequency of this is going to pass that, and you're going to get a very nice clean sine wave coming out. So by adding a low pass filter, a first order low pass filter to that, you can actually get now 3 waveforms coming out: a square, a ramp, and a sine wave coming out of it. Right, and this is the kind of circuit, when you go into the lab and you hook up a signal generator, you notice that the signal generator has some switches in front, and you could get square, triangle, sine wave coming out of the terminal, depending on where you press which button you press, right? In fact, it is using a circuit, a modified circuit like this. Of course, and you put the filter here, and here you could get a sine. Here you get the square, and here you get the triangle coming out. So depending on what switch you press, it connects to the output here, here, or after the filter here. And you select the frequency. When you turn that dial, what you're changing is this. You're changing that resistor. So if I put a variable resistor here, if I vary that, I'm going to be able to vary the frequency of the oscillator, and I could get a variable frequency triangle, square, or sine wave coming out of it, right? And they put some extra circuit inside of that box on the desk. Is some circuits to adjust to amplify the sine wave a little bit, so you could get you could get variable amplitudes coming out of it, and to buffer it a little bit so they could drive circuits without loading down and so on. But essentially, that is the basis of that device that you see on the desk when you go and sit down in the lab.
So as we're on this page, just one quick question. The R and NR, right? Those resistors, those just dealing with the gain.
This one?
With yeah.
Yeah, this is a particular type of thing called a comparator with hysteresis, right? In other words, it gives you a little bit of a deal. It has a little delay when it toggles, so that it gives the circuit. Remember, all of these devices have a little bit of a propagation delay. When it switches from positive to negative, negative to positive, it takes a little time to do that. So to give the capacitor and to give the integrator time to respond, the comparator with hysteresis basically doesn't switch. When it switches from positive to negative and negative to positive, there's a little delay in it. That is a hysteresis delay, right? And you could add as much delay as is required to get the circuit working. And of course, it also gives, that resistor also affects the amplitude that you could get out of this. It's setting the upper and lower amplitude as well. All right. So like for here, if you change the ratio n for it, right, you could get it to go up and down, something looking like that. All right. There's a limit, of course, because you can't go beyond plus or minus VSAT anyway, right? So that's governed inside of here, right? So VSAT, in fact, kind of determines what N is, and N determines, once you have a resistor and a capacitor, N kind of determines what frequency you could get out of it as well. All right?
Okay.
So the first thing you do when you're designing the circuit is to get that NR and R to kind of get that ratio down. Usually it's 2 or 3, it's not more than that. And then once you have that 2, 3, 4 kind of thing, you're not going to get N being 100, because if N is 100, then look at what happens here. If N is 100, then, and the output here is, let's say, 9 volts, then V low threshold is going to be that divided by 100, which is very small. The bigger you make N, the smaller the amplitude of the triangle wave coming out. Right? So as N goes up, this thing starts to get smaller and smaller and smaller. Right? So it will start to do this, do that until it becomes useless. Right? So normally N is typically 1 to maybe 4 max. Right?
Makes sense.
Yeah, you can see it here. Look, this one. I can't remember what value, and this was something in multisim. But you got to work it out from here, right? You got to work it out from here. If you look at the output here, this is about 11 volts maybe, and this here is about what's that looking like, 2.5,
Yeah.
Right? So N is about 11 over 2.5. You can see whatever that is.
4.4.
Right? Yeah. 4 point something. Right? Right? So you're right.
I don't think I'm ready as yet to write the
So,
exam.
so this slide, right? The part where them, yeah, the part where them say the comparator output snaps positive to plus VSAT. What's going on there? That is when the square waveform going up to
from minus VSAT to plus VSAT.
For which point it's starting at?
It's starting here, you remember? Okay, if the waveform doing this, right? The output of the comparator is at this point. So it's at minus VSAT. As soon as the output of the what do you call it? That triangle wave, as soon as it crosses this threshold, which is the input of the comparator now, then this voltage here, the output, remember, it's a comparator. So as soon as this voltage crosses this point here, right, the output going to snap or suddenly jump from negative to positive. Right? This is fed back, so this is a positive going step. The integrator produces an integral of a positive going step, but inverts it. So you get a negative ramp being created here. Right? Until it reaches a negative threshold value on the comparator. And then once it reaches here now, the comparator voltage will snap or change suddenly back from plus VSAT to minus. That is fed back. This is a negative going step. So that the integrator integrates that, but it's an integrator with an inversion in it. So instead of giving me, normally this would give me a negative going ramp, but because I've inverted it, I get instead a positive going ramp, which is this bit here. Right? And the process just repeats and repeats and repeats. Yeah?
Yeah, I was kind of confused because I noticed part of the square waveform kind of cut out from this graph now.
Where?
And you see like that space.
Like here?
Not there, right? And you see it have a space in between.
Yeah?
Yeah, that space.
That's really letters.
Letters. Right when we were putting in the this is what it really looks like. That is the actual plotting. Right? This was generated from multisim. You put the circuit in multisim and run it. This is what they get. Right? So short of going into the lab and taking a picture with the scope, this is what the simulated circuit, but the actual waveform based on simulation should look like.
And when the square waveform ready to decrease, right? Well, to go back to negative VSAT, right? It started at the middle top at VSAT.
Yeah, once this, right. So this is what is causing this to happen. Eh? So when this reaches this voltage here, whatever is this threshold voltage here, we said it minus 2.5, it looking like. Once it reaches minus 2.5, that threshold causes the comparator, which is sitting down here, to suddenly go from plus, let's say 11 volts to minus 11. And that step change from plus 11 to minus 11 is integrated and inverted by the integrator, and you get a ramp going positive now. So it starts ramping back up now until it reaches plus 2.5. And at that point in time, the comparator snaps now or changes from minus 11 volts back to plus 11. Right?
Yeah.
You sure you understand, Camraj? If you don't understand, I probably could explain it in a much, well, I don't know, simpler, but a way that you might understand a little better if you have any problems.
So it's saying it's starting, when it's ready to go decrease, right? To VSAT, it will start at the middle point, decrease all the way to the other connected form in our next cycle.
Well, it's not decreasing necessarily at the middle point. It decreasing as soon as it saturates at the beginning of the op amp. So if you go back to the circuit, so the 2 op amp, right? Yeah. So
just let me just clear this a little bit. Good.
So once you see how it have an output by V compt, that is being fed back into the integrator, right? Now the integrator, it does turn the ramp, turn a signal into the ramp, right? The square into the ramp. So it is negatively inverted. So once it have a positively saturated input here, it will have a negative ramp. You get that, Cameron?
That is this bit here.
Right.
Right. So if you have a positive input to the integrator, this is the integrator here. Right. If the input to the integrator is positive like this, the integrator integrates a positive step but inverts it because we have this set up as an inverting arm. So you get a negative going around. Right? And then what I was telling you is that if I take this now and do this, then this is going to do that for me. Right? Yeah?
Yeah.
And why you're seeing this is 5 volts here, why you're seeing the square wave smaller is because it coming from a power source, like a voltage source, and not a next op amp with a VSAT signal.
Right? Forget this a little bit. This was a simulation where I used 5 volts. The circuit diagram has 1 volt here. So if I were to do it with this circuit diagram, the circuit diagram would have been, as we have it here, would have been from 0 to 1 volt instead of 5. All right? Okay?
Yeah.
Anything you don't understand, Cameron?
And then this is mechanically. So if I'm switching from one to the other, I get this. And if I kind of make this time, if I reduce this time, then this point here will get closer and closer to here, and eventually I could get this. Right? And then if I switch it exactly correctly, I could get that, which is a triangle wave. So to do that, what we did is to add this extra little bit here. So this whole comparator is giving me that square wave going positive, negative at exactly the right point. So it is timed in such a way that when this goes up, and then it will switch down and switch up exactly at the correct points when this is changing, kind of. Yeah.
Yeah, that makes sense.
All right. Okay, so let me stop sharing here. Actually, I just got a call. I have something here. It's 11 o'clock here. I have to go and do something for the office right now. But feel free to contact me as well. Well, Cameron kind of volunteer to help you, but if anything's still not making sense, let me know and I will discuss it. Friday, we wouldn't have a class on Friday morning because I have there's another meeting that I have to go to. But I'll answer questions and we could probably meet next week again if you all want. we're still waiting. I'm still waiting to confirm the time for the face-to-face exams for you all. And as soon as I know it, well, of course, you all will know probably about the same time anyway. Okay?
All right.
All right. Okay, so